All right, section 2.1 is titled The Derivative and the Tangent Line Problem. We've seen a little bit of this already. We've talked about it sort of as in vague terms, and we're going to talk about it in much more specific terms today. So we encountered what we would call a secant line and a tangent line back on the very first day of class. I drew some pictures for you, and I'm going to draw those pictures again, but they're going to have a little bit more detail to them this time. So I'd like for you to draw a graph, and the graph will look roughly like this. And I'm going to draw this graph. I'm going to copy and paste mine. I don't have to draw it again. All right, so on the left-hand side, I want to mark a value C. So we'll call this point C. And we'll call some other point over here C plus H. So the distance here apart is H. That's why it's C plus H. And it's about right here on my graph. All right, everybody good so far? And if we were to correspond this to the y-axis, this one would be f of c, if my function's name were f of x. And this point slightly above it would be f of c plus h, because that's the x value. And I'm using the name f of x for my graph, obviously. So a secant line here would be the line that connects these two together, regardless of the fact that the graph itself is not a line. So my secant line would look something like this. Okay, does everybody remember that? I've drawn this picture before, not with the details of the H's and stuff on there, but the rest of it I have. Okay, if we were to take this same graph, I'm going to actually start over again. Let me copy with all the details. So if we were to take this same graph and we were wanting to know about the tangent line, well, the tangent line should be a line that's sort of just touching the curve instead of cutting through it like this. Are you guys with me? Yeah. So the tangent line is the idea of letting this value h that I'm far enough away from get closer and closer to the value c. So instead of the value h being where I've currently placed it, you know, this distance away, maybe instead I'm right here. So now this right here would be c plus h. Could I draw a secant line through those? Sure could. In fact, I'll draw it right now just for the sake of the picture. Obviously, the secant line looks different for that one. Oops. It looks almost like that, right? Because the points are closer together. They're on a different part of the curve. But what if I let the point get even closer? Well, now maybe I'm right here, my blue point. Okay, well, I can draw another secant line there, right? No problem. So that secant line would look more like that. Whoops. Let's try that again. Something like this. And I could keep letting that distance h get smaller and smaller and smaller. And eventually those 2 points would get so close together that it almost looked like one single point. Are you with me? And if I could do that sort of infinitely many times, let it get infinitely small, that value h, how far I am away, what I would arrive at is I would arrive at the limit as h goes to 0. It's a limit, and that would be the tangent line. Okay? So I'm letting the distance get infinitely small. That's a limiting process, and I approach the tangent line as I do that. So the slope of the secant line through these points, the way we find slope, is that we take f of c plus h minus f of c over c plus h minus c. And if you notice, this is the same standard definition of slope that you have grown to know and love throughout your life. It's just that it's using specific values. So this is y2 minus y1 over x2 minus x1. It's just that the c value and f of c are the x1, y1. And this distance that we are away, c plus h, are x2 and correspondingly y2. So we're just subtracting y values and dividing it by subtracting x values. Now, of course, we can simplify the denominator. I have c plus h minus c. That just subtracts out and we get just h, right? So this would be the slope of the secant line. Any line we can do this for. H can be any value that's not 0, because it can't actually let 0 be in the denominator, right? This would work for us. All right, so then, the definition of the slope of the tangent line is quite similar. You'll notice that this part of the equation is exactly what was on the previous screen, isn't it? F of c plus h minus f of c over h. What's different? The limit, right? This notation at the beginning is new. It says the limit as h approaches 0. So if f is defined on an open interval containing c, that should sound familiar, right? That limit definition that we had back in chapter 1. And if the limit exists, then the line passing through c f of c with this slope is called the tangent line to the graph of f at the point c f of c. This slope of the tangent line to the graph is also called the slope of the graph. So if you hear the phrase slope of the tangent line or slope of the graph, they mean the same thing. Okay? So what we're going to be doing in this section, so just to show of hands really quick, who's had calculus somewhere in your past before? About half of you, that's what it usually is. Those half of you have to put aside what you know about finding derivatives at this point. Okay? We're getting there. Like soon, like 2.3 or 2.2, we're almost there. Okay? You have to put it aside for the moment. What we're going to be doing is we're going to be doing the limit definition for what that is right now. Okay? And if you haven't had calculus before, then none of that made any sense, and that's totally cool. Okay? All right, so what we're going to do is we're going to find the slope of the tangent line to the graph using this definition. And you will all appreciate the rest of what we do in the chapter after this so much more after today.
Yeah.
Okay? After today, I think Wednesday too, actually. I think we spend a couple days doing this. Okay, so what are we going to do? We're going to do that definition that we just had on the previous slide or screen. And that definition said the following. It said the limit as h approaches 0 of f of c plus h minus f of c over h. And this is at some value c, so some x value that's equal to c. So as you take a look at this particular function, they give you the x value. What's the x value in this particular case that we're looking at? It's 1. So as I'm looking at this, I'm going to be using the x value of 1. I don't need the y value they gave me at all, okay? So we're actually going to be finding, the notation is actually a prime notation. It looks like this. We're going to be finding this notation, which is the slope, at g of 1. So the definition says I'm going to do the limit as h goes to 0 of my function g. So this is g of 1 plus h. All I'm doing is replacing all that notation where it said c with 1 minus g of 1 over h. And if you use the f instead of the g here, it's not a huge deal. Okay, our function name on this one is g. The function name in the general formula was f. It doesn't matter to me. Okay?
We need to put the little 1 on top of the g.
It's actually not a 1. It's almost like an asterisk mark, or not asterisk, an accent or an apostrophe is what it actually looks like. It has more of a slant to it a lot of times when you actually see it written down. It looks more like that. But for right now, no, but we'll be using it significantly in the future, so if you want to just go ahead and get used to it, now's a good time to do that. All right, this right here, before we do the limit, is algebra. Okay, we actually teach it on campus in our algebra course. It has a name. It's actually called the difference quotient. And the way we calculate it is we have to remember function notation. Now, in particular, this piece right here, you know what the g function is. It's 6 minus x squared. So how would you find g of 1?
Just plug it in.
Just plug the number 1 in for g, or in for x, into the g function, right? But you do the same thing for this one. But you don't plug in 1, you plug in 1 plus h. All right, so the first thing we're going to do is this sort of evaluation step or substitution step. I need to take the g of x function, which is 6 minus x squared. But my x is 1 plus h squared. So all of that is this piece right here. It's not simplified, but it is the value. The second one is to take 6 minus x squared, but the x value is 1. Yes. You're going to have to write something of it, whether you write it like, hang on a second, I left something off, so I'm moving it. Whether you write it here or whether you write it in the next step, you're going to have to write something of this. And the step that I left off was the one I was already so kind of harsh about you with on your test, that limit step. It's still there because I still have an H in the problem. Okay, as long as I have H in the problem, I have the limit in front of it. Okay, let's do the easy part. The easy part's this one.
Why couldn't you just plug in the 5 instead of writing it
Because, oh, you could. It would be the same thing for that, yes. Some problems will give you like the 0.15, others won't.
Yeah.
And in general, we don't always have a point. I'll show you that in a minute. Sometimes you're just told to do it for all x values, and you won't have that piece either. So, yeah, this is the part that's the easy part. You're right, though. It's 5, right? 6 minus 1 squared is 5, and you also know it's 5 because they actually gave you that right up here. Yeah?
True.
So that piece is 5. That's no problem. I still have the limit as h approaches 0. I have more that I'm going to write down here in a minute, but I have 5 at the end. Okay, so what do you get when you take 1 plus h and you square it? You have to FOIL it out, right? So it's not 1 squared plus h squared. You have to FOIL it. So you do 1 plus h times 1 plus h. So I'll write that stuff down. Let me see if I can remember if I do. I don't. But I've got space over there, so it'll work. So here's my 6, and then I have 1 plus h times 1 plus h. Don't let the common algebra errors trip you up.
You don't actually want us to.
You do not have to write that, but I do want you to FOIL it, yes. You will not be able to work the problem out if it's not FOILed next. So this would be 6 minus, what's 1 plus h times 1 plus h?
Should be 1 plus 2h plus h squared. H squared, right?
Yeah, in either order would be fine, sure. Okay, is everybody good with that step? 6 minus 1 plus 2h plus h squared minus 5 still and over h. Okay.
6 minus the parentheses still supposed to be in brackets?
You can. It doesn't really matter because eventually they're going to come off anyway. So if you want to leave them in brackets for now just for organization purposes for yourself, you can, but you don't have to. I'm copying and pasting this to the next slide so that I have more space. So don't go worrying about typing what I've got on the next, writing what I've got on the next slide type just yet. We'll get to it, but just let me have some space for a second, okay? Okay, so continuing with this, what's my numerator going to simplify to? Well, I have 6 minus 1. That sounds a lot like 5.
Negative 2h.
Negative 2h
Minus h squared.
minus h squared.
Minus 5.
Mm-hmm.
5h.
Okay, now what do you see?
Cancellation.
Cancellation. What can cancel?
5,
Minnie?
negative 5, and h. On the bottom.
Okay, so the 5 and the negative 5, those add to 0. And then if you've done the problem right, everything in the numerator should have an h in it. Does everybody see that? Okay. That means I can divide an h out of everything. So be really careful when you do that. I know we love to use the word cancel. The problem with the word cancel is sometimes things cancel to 0 and sometimes cancel to 1. So you're really dividing the h out. Yes, Dawson?
If we're going to take the h out, finally, do we have to put the limit?
You will for one more step. Yeah. So this h is divided out of each term. What that means is that what I'm left with is negative 2 minus h. Does everybody see where the negative 2 and the minus h are from?
Yes.
Excellent. This is the step where you can stop writing it, Dawson, because now we're going to plug in 0 for h, and if I plug in 0 for h, what do I get? Negative 2. And this is g prime of 1. It's the slope of the tangent line of the graph. Yep, you can. We're not going to use the word actually in the book until the next section. Actually, that's not true. I think it's the next page. It is. It's the next page. Now you can use the word. Okay, this word is actually on the next page. It's on this screen, definition of the derivative. So go ahead and fill in the details on this one. The derivative of f at x is f prime of x equals, the limit as h goes to 0, of f of x plus h minus f of x over h, provided the limit exists. For all x for which, I don't know, your books or your paper says or which, but it shouldn't say or. It should say for which this limit exists, f prime is a function of x.
Is that what that little apostrophe is?
Yes. Yes, it is. Now, take a look at this and compare it to this. Pretty much the same thing, right? What is different notationally? There's a prime notation. There's something else too. The what was it, Fallon?
Well, it changes from f to c to f of x.
Yes, that's exactly what I wanted to point out. You'll notice on this one it has the value c in it, and over on this one it has the value x in it. This definition over here said it works for a specific point c, f of c. And this piece over here, this definition says it'll work for everywhere where it works, which is fantastic, right? It'll work everywhere it works. It's saying all the x values are fine to do this at. And in particular, what it means is this problem that I did, where I did it specifically with the value of 1 plugged in, that's okay, but I also could have used x where I had the 1, and in the very end plugged the value for 1 in, and I would have gotten the same thing. And I'll show you that on the next problem. Was there a question over here? Okay, I thought I saw a hand. Okay, so very little is different with this definition than before. The biggest difference really is that I don't need a number to be using this particular formula. C was a number, x is a variable.
So could you use like an imaginary?
No, we're just going to use x.
Okay.
We're just going to use x.
But could you, theoretically?
But that's what x is. I don't want you to use the word imaginary because imaginary has a meaning in mathematics.
Okay.
Calculus doesn't use imaginary numbers.
Oh, okay.
Yeah. So I don't think that's actually the imaginary you meant necessarily,
No, I meant
but
like the little I.
yeah, we don't want to use I.
Okay.
I definitely has a meaning in mathematics.
Oh, okay.
X means variable, so it means any value, and that's what we're going to be using is the x. Okay, this one says find the derivative by the limit process. Okay, we're going to use this formula that's in the box right here. Okay, so the first thing I'm going to do is I'm just going to write that formula on the other screen. So I want to find the limit as h approaches 0 of f of x plus h minus f of x over h. And this is f prime of x. That's what I'm looking for. This is just copied from the page before. I would write small because this problem takes several steps. So in your space, you can see my paper right here. Do you guys see? We're just going to take a few steps. Yes?
Is this going to be like last chapter of the test where we have to memorize? I know I'm sure we have to memorize that, but are we going to have to memorize the whole word definition of that?
You will be memorizing this definition right here. Yes.
No, what about the one before that?
You don't have to. Just this one's fine. Yeah. So yes, on the next test, this is one of those things that will say memorize this, and I will ask you to write it down. Yes. Okay, you're going to use it so many times between now and then, you're going to memorize it anyway by default. Okay, so notationally, this piece is the easiest piece because it's right here. I don't have to plug any numbers in. I don't have to do anything. I just take where the red is and I do a replacement. It's a substitution. So in terms of writing this down, remember every step is going to have limit h approaches 0 on it. The denominator doesn't change. And in the numerator, the second piece of the numerator is going to be 1 over x squared. Okay? That's just a replacement. That's all it is. The other portion requires a little bit more work because there's sort of two replacements. What you're needing to do is you're needing to replace, in the formula that's highlighted in red, you need to replace where the x is with x plus h, and then you need to write it right here. So it's sort of this double replacement. I'm replacing this piece with what this is, but this is this piece with the number x plus h plugged in. Okay? So all of that complicatedness to say that what I'm going to have written down here is 1 over x plus h quantity squared. It's the same equation, 1 over x squared, but I don't have x in it. I have x plus h. Okay, so far so good? That's all algebra substitution kind of stuff. Okay, the limit part at the beginning, that's the calculus part, but what I just did so far is algebra.
So you just put the x plus h into the...
Into the equation f of x. Okay, we're going to do a lot of algebra cleanup on this one, and that's going to be the name of the game on all of these is cleanup with algebra. So I have 1 over, what does x plus h quantity squared look like? X squared plus 2xh plus h squared, and you get that by distributing, right?
Yes.
Foiling might be a word you're familiar with. And then I have minus 1 over x squared, and it's divided by h. Now, the name of the game, the goal here is I got to do something to get this h to go away. Why is that h my problem?
Because it's 0.
Yeah, because my goal eventually is to put 0 in for it, and I can't do it as long as it's in the denominator.
So,
Minnie?
does it matter if I put 1h over to the left or the side?
We can do that. Yes, and we will in a minute here anyway. But so Mooney was asking, instead of writing this sort of as a double fraction, could I sort of move it up as 1 over h on the side? And I will in a second here, yeah. Did you have a question over here? No? Okay. Okay, so let's see where I am. All right. I can't remember if it was in this class. I don't feel like it maybe was. But you probably have heard something along the way that says that these double fraction things are not so very friendly. That's kind of what you're saying, even by saying, can I just not move it somewhere else? We don't want double fractions. But the only way to get rid of double fractions is to somehow combine the fractions that are already there. So whether I move this h up now and kind of set it over here, or whether I do it later, somehow these two pieces are going to have to be combined into a single fraction. How do you combine or add two fractions together? You've got to have common denominators. And these two denominators don't have any factors in common, right? They've got pieces in common, terms in common, but not factors. So the best we can do is simply multiply them by each other. Okay, so I will do one step just so that we can say that we did it. I can write this with the 1 over h over here. That's fine. It still doesn't fix anything. I can't let h be 0, yeah? But I can write it that way to save a little bit of space. Okay, so I do need common denominators, and because the denominators that I have don't have anything in common, I'm just going to have to let them be each other. So the first piece is going to be multiplied by x squared over x squared. And the second piece by x squared plus 2xh plus h squared. And x squared plus 2xh plus h squared. You don't necessarily have to write that down. I just want everybody to see what I'm doing before I have my next step. So this one's going to have x squared in its numerator. And the other one's going to have the other piece.
Its limit goes to h to 0. On the bottom is that limit of x equals 0 or h equals 0.
Did I change it?
Yeah.
It's h. Thank you. Moving too fast. Yeah, it's still h. Thank you. Okay, so the first numerator becomes x squared. The second numerator becomes x squared plus 2xh minus h squared. Plus h squared. It's still all subtracted. The common denominator now is x squared plus 2xh plus h squared times x squared and times the h that's on the outside. Okay. It would be highly unproductive and unhelpful to multiply that denominator out. I would strongly encourage you not to do that. Now, I would encourage you, however, to simplify the numerator. Do you see some pieces in the numerator that are going to simplify?
h.
Not the h. Oh, I messed up, though I did mess up on my numerator. I left an h off. Let me fix that. 2xh plus h squared.
It's gonna be the x.
Yeah. I've got an x squared here, and I have minus an x squared here. Those pieces are going to add to 0, right? And then this negative will distribute through the rest of it. Let's see if I have any more space. I don't. Man, I have got to change these slides to give myself some more space. Let me do this for now.
Whoa,
Isn't that the coolest?
that's awesome.
Yeah. So I just sort of found myself some more space, didn't I?
Yes.
Yeah. It's good because I was out. Okay. So over here, the limit as h goes to 0. Like I said, I've got x squared minus x squared, so those are adding to 0. And then I have negative 2xh, negative h squared, over x squared plus 2xh, or 8hx, either way, plus h squared, x squared, and h.
What if the h ended up next to the denominator earlier?
Earlier it was underneath. It was written as divided by h, but dividing by h is the same as multiplying by the reciprocal. Right? Dividing by 2 is the same as multiplying by 1/2. That's the idea. So you're just writing it as a multiplication fact instead of a division fact. Yes?
Oh, never mind. That's confused.
Okay.
You
Any other questions about where pieces came from or anything at this point? I definitely want to answer those.
Yeah, I'm kind of wondering.
Okay, which piece,
what
Dawson?
just happened.
I distributed the negative. Kind of wondering what had just happened. That's a good question. I distributed the negative like this.
And
So
then
this negative
took out the x
added these to
squared.
0,
Okay.
and then this negative gave me a negative 2xh, and this negative gave me a negative h squared.
Okay.
And you can take more steps to write that out if that's more helpful for you, for sure.
Okay.
Okay, any other questions? Does anybody see what helpful thing happened? Madison? I did. I multiplied the top by 1, which doesn't change anything, and if I multiply the bottom by h, I just put the h next to it as a multiplication factor.
So are you
So,
gonna
yep.
cancel an h now?
Yes, sir, I am. Do you see how everything in the numerator has an h in it? Do you remember I told you that would always happen?
Yes.
If it doesn't happen, you've made a mistake.
Okay.
So kind of like one of those red flag moments, and you're like, okay, well, I did something wrong because I don't have h's canceling yet. Okay, so everything in the numerator has an h, and there is also an h in the denominator.
Yes.
So I can divide out an h from all those terms.
Okay.
So this h, one of these h's, and this h I'll divide out, and that's what I needed to have happen. Because that's the h that was not allowing me to plug in 0.
Okay.
Okay?
One more question.
So let me write what I have left first a second, Dawson, and then I'll let you ask.
That was my question. Do we
So I
ready?
have the limit as h approaches 0. I've got a negative 2x minus h. I do still have an h in the numerator, okay? And I still have an h in the denominator. I have x squared plus 2xh plus an h squared, and I have an x squared. All those pieces still remain. So the problem is not the h in the denominator in general, it's the fact that the h in the denominator is multiplied by everything else. Okay? Because at this point, we can actually take the 0 for h and we can plug it in. Okay? So I can actually write down that I have negative 2x minus 0 over x squared plus 2x times 0 plus 0 squared. All of that is multiplied by x squared. So I do have some pieces becoming 0. It's just the whole denominator is not becoming 0, which was the problem. So my numerator is negative 2x. My denominator has an x squared and another x squared in it, doesn't it?
Okay.
So why didn't the h come out of the parentheses when you took out h?
Because we're dividing everything in the numerator by h. So this term gets divided by h, this term gets divided by h, but everything in the denominator is currently multiplied together. So when I divide the whole denominator by h, it cancels with the factor of h that's in the denominator. Okay? You guys do it with numbers all the time. It just feels funny when we do it with variables, but you do that with numbers. Yeah, it works because it's a factor, and the factors are represented outside the parentheses. You're exactly right. Can I simplify negative 2x over x squared times x squared?
Negative 2x.
Yes.
Negative 2 over what?
X cubed.
X cubed. And this is the derivative for the problem. And that's a long way to do that problem. It is.
I just can't wait.
Yes, it is a long way to do that problem. Okay. All right, so here's the deal. We're not going to get this one finished today. Let me pause right here.